Okay. So in this session, again we will be looking at chapter 13 only, in which we will discuss the magnetic effects of electric current. Okay. So in the previous chapter we learned how the electric motor, in the previous session we learned how the electric motor works and all, right? In this session, what will we learn? Let's take a look. We are going to learn electromagnetic induction. We will see an experiment and we will also look at the Fleming's right hand rule. Okay, we will learn the Fleming's right hand rule. And then we will look at an electric generator, how the electric generator works. Okay, because this is also very important. It works. The working we will look at. So let's start with the experiment. Okay, so remember the Fleming's left hand rule. What did the rule tell us? That in the presence of a magnetic field, if there is current flowing in a conductor, then there is a force applied in the conductor. Okay, right? And the left hand rule told us the direction of the force which is applied. In this, what people thought after that is it possible that in the presence of a magnetic field, okay, if there is force applied in the presence of a magnetic field, current generated in a conductor. So as you can see in this setup, in this experimental setup, you have coils which this conductor, okay, it's wound in this particular format. It is like a solenoid, a little bit like a solenoid, remember? And it is connected to a galvanometer, which will tell us when the current, if there is any current generated. What we are going to do is we are going to introduce a magnetic field near this conductor. We're going to put a magnet in and out. Okay, we're going to keep moving it in and out. So there is force applied and the magnet is what is going to give us the magnetic field. And we will see if there is current which is seen, if there is any current flowing through these conductors. Okay, that is what we are going to look at right now. It is called electromagnetic induction. If that is what we are going to see with the experiment. Let us see what the experiment is about. There, as you can see, this person is bringing a magnet into the coil. Okay, and see, when he brought the magnet into the coil, that is when there was some force, when there was some movement, the galvanometer showed some deflection, right? This deflection means that there was a current which was induced. So now if he is moving it away, again there is a deflection that you can see over here. Okay, and that means there was again a current induced. So the deflection in the galvanometer shows up in the opposite direction. This means the current is set up in the opposite direction. So that is another thing, like when it even in the other case, when the current direction changed, the direction of the force changed. So in this case, when the direction of the force is changing, the current direction will change. Okay. Okay. So now let us look at Fleming's right hand rule. Okay, can you see the hand over here? So according to this, we will use this hand to learn the right hand rule. Why are we learning the right hand rule? As we saw in the experiment, in the presence of a magnetic field, okay, if we move a magnet, okay, towards or away from a particular a circuit, there is a tiny amount of current generated. So this right hand rule tells us what is the direction of the current generated when we apply some force to the conductor in the presence of a magnetic field. So as you can see over here, in the magnetic field, we are putting some force, okay, because of which the current is flowing. In that particular particular pipe that you can see, that is a conductor, which is why there is current over it, because in the magnetic field we are pushing it upwards. So what do we see? If we keep the thumb, which is the pink finger, in the direction of the force, and if we keep the yellow finger, that is the index finger, in the direction of the magnetic field, then this blue finger, okay, will show us the direction of the current. So that is your Fleming's right hand rule. This is the principle that is used in an electric generator. We'll see how. But before that, let's just review what is right hand rule. Right hand rule is that the pink finger, which is the thumb, should be kept in the direction of the force. The magnetic field direction is shown by the index finger. Then the blue finger, which is your middle finger, will show us the direction of the current. Alright, so that is your Fleming's right hand rule. So as you can see, in this, if we keep this rod and we push it upward, okay, in this magnetic field, which is going from the north pole to the south pole, then the current will start. Current gets induced in it. So a current has now started, and the current is in towards you. The direction of the current is out of the screen. Alright, so this is Fleming's right hand rule. So in this, now we're going to start studying about an electric generator. What is an electric generator? It is how we create electricity, okay? It is where we create electricity. So there are this electric generator works in the based on the principle of the Fleming's right hand rule. What does the right hand rule tell us? It tells us that if there is a magnetic field and there is force being applied, then there is the direction of the current is what it tells us, correct? So what we are going to do is we are going to see how the that particular an electric generator works, okay? So all of these have this particular motor in between. Not motor, I'm sorry. Okay, so let us see. In this case, we have a rectangular coil. Okay, the magnetic field is flowing from the north to the south, the direction of the magnetic field, and there is a rectangular coil in the magnetic field. Okay, what we will do is we are going to artificially move the coil so that current is generated. Alright, now why are we artificially moving? There is no how in the motor there was current which was being supplied and we were looking at force. In this case, that is not how it works. We are going to generate the current, which is why it is called an electric generator. So to generate the current, what we are doing is we are going to see what happens when we move the coil. Okay, so let us so the coil will move like this. Okay, now when the coil moves like this, current is generated in it, and we are going to take that current and connect it to a smaller circuit where we will use that current to get light or whatever. Okay, so this is how it works. We will look at different aspects of the circuit very soon. So this is an electric generator. Now let us remember remember the right hand thumb rule, Fleming's right hand thumb rule. So the right hand thumb rule told us that if force is applied upward and the magnetic field is in the direction of the index finger, that is to your left, then the current will flow out of the screen. Okay, so let us use the Fleming's right hand rule. Sorry, not thumb rule, right hand rule. Okay, let us use it along with our coil and see what happens. There you go. So in the pink line, okay, we are going to use the right hand rule. So in the pink coil is moving upwards. That means the force is in upward direction. Okay, the magnetic field is in the index finger direction, which is from north to the south pole, north pole to the south pole. Then the direction of the current is into the screen, right? Similarly, in the blue line, okay, along the blue line, if you look, the force is applied downward, correct? That is why it is moving downward. Remember how in the electric motor the board we saw? So it is moving downward, and the index finger shows the direction of the magnetic field. So then our middle finger is showing the direction of the current, which is out of the screen. It is going to flow outward. All right, so this is our right hand thumb rule. This is what we found out. So now let us put arrows to tell the direction. There you go. Pink is into the screen and blue is out of the screen. Okay, so how downward force, I is out of the screen, upward force, I is into the screen, I is current. So now what we are going to do is, there you go, we have put the arrows, okay, and the arrows are now showing us the direction of the current. So this is how it moves. Now once it comes perpendicular, which is one half of the circle is over, what happens is the pink line comes to the south pole and the blue line goes to the north pole, just like back in the generator. Okay, we are rotating the this particular rectangular coil, right? So now the magnetic field direction has not changed, it is still from the north pole to the south pole. Okay, and but now what will happen is the current direction will change. Okay, why? Because now the like, see, there you go. Now the force is like, we already know that when the blue line was on this side, right, blue line was near the south pole, the current was out of the screen. See, now for the rotation is happening, which means in the pink line, now when it is near the south pole, the force is down, force is downwards, which means the current will be out of the screen. That means the direction of the current changes. Same way, the blue line is now close to the north pole. Okay, and what happens? The force is upwards, correct? If it is upwards, the current is into the screen, right? So the current direction changes. Up and into the screen, down and out of the screen. Now the current direction has changed. Okay, there you go. So in every rotation, the current direction keeps changing in every half rotation because of the force that we apply. Okay, so now we can see that the current direction changes. Let us connect it to an outside circuit. Okay, there you go. If we just directly connect, again the same tangling issue will happen. Like, now the wire will cross each other, so that we don't want, right? I mean, that is going to cause issues. So what we will do is, we will use rings. Okay, 2 rings we are using. Now we'll see why we are using 2 rings. Okay, so this pink ring is connected only to this pink line. Okay, only to the line in the left, and this blue ring is connected to the line on the right. Okay, the pink ring is not connected to the line on the right. Now again, just like how in the motor, these are brushes. Okay, they are called carbon brushes, and these brushes are simply touching the rings. When the coil rotates, the brush will keep touching the ring. It is so that the tangling does not happen. We learnt this in the previous session. So like, let me show you. Remember this picture in the bottom about the ring and the brush. So when the ring rotates, the brush simply stays put and touches the ring. All right. So now so now what happens, where in the pink line we saw that the force is upward, so the current is into the screen, correct? And in this blue line, since the force is downward, the current is out of the screen. Okay, it is coming towards you, direction of the current. Now because the pink line is connected to the like pink ring, okay, that means the current direction has to, since the direction of the current in the pink line and the blue line is like this, the current direction has to be like this in the yellow line, right? It has to go from the blue line, touch the since it touches the blue ring. Okay, since the blue line is in contact with the blue ring, from the blue ring the current comes and goes via the bulb into the pink ring, okay, where it will flow like this. So the circuit is also complete. Okay, so there you go, and it is rotating. Now when it rotates and it comes into the other end, okay, the other configuration, that is when the the pink line is closer to the south pole, the current has to be out of the screen, that is towards you, correct? So now the current goes that way and touches since the pink line is connected to the pink ring, it touches the pink ring, and from the pink ring the current flows in the opposite direction in the yellow line, as you can see in the circuit. So in this case the current was flowing in this direction, okay, in this direction from the blue ring to the pink ring. After the rotation it flows from the pink ring to the blue ring, because the direction of the current changes in the rectangular coil, which we already discussed was because of the force applied. Okay, now as you can see, every half turn, okay, the current direction changes, right? It is changing from left to right, or it is changing from blue to pink to blue. Okay, this is why it is called alternating current, because the current is alternating between the two directions. Okay, we use this alternating current, we generate alternating current, and that is what we supply to homes. Okay, we supply it to homes. Now this much is what alternating current is about. So assume that in one particular direction the bulb glows yellow, and in the other direction the bulb glows blue. Like, let's see. Okay, so in this direction, when the current is flowing from the pink ring to the blue ring, okay, if the bulb glows blue, and in the other direction, when the current is flowing from the blue ring to the pink ring, the bulb glows yellow. Okay, so the current direction is alternating, which is why the current which is generated, okay, via this method is called alternating current. Okay, alternating means it keeps changing, okay, between two things. It keeps changing between two things, and it is called alternating current or AC. Okay, fine. Now what if we didn't want to change this direction of the current? What if we always wanted the current to be in one direction? So for that, what we do, by the way, whatever generates alternating current is called AC generator. Okay, because it is creating alternating current, which is the direction of the current keeps changing, correct? So okay, now what if we didn't want to change the direction of the current? We always want the direction of the current to be from your right to the left. Okay, we want the direction of the current to flow from right to left. So what do we do? Okay, remember those split rings that we used in the generator? We're going to use those here. Okay, because again we don't want any tangling, and we know that the current direction changes, which means we have to ensure that this carbon brush is always going to be okay, so since the current is flowing from the left to the right, what does that mean? That the left is positive and the right is negative, right? That means I always want this carbon brush to be negative and this carbon brush to be positive, like the negative and positive terminals of the battery we are trying to create over here. So what we'll use is these split rings. These split rings, because of the split in between, it will let us do the thing that we want it to do. That is, change the this carbon ring should always be negative, okay, which is so that like the direction of the current so the direction of the current stays the same. Okay, so because of the hole in between, they are called split rings. So as you can see, since even when the current direction is changes in the pink line, okay, when the direction of the current changes in the pink line, the pink half of the ring comes in contact with this brush. So basically what happens is this brush is always in contact with the line through which the current is coming into out of the screen, right? It is always in that particular line only. So which is how we will generate current in one direction. That is called direct current. Okay, alternating current is when the current is in two different directions. Direct current is when the current is in one single direction. So that is why this is called a DC generator. This is how a DC generator works. A direct current generator works with the split rings. So in an AC generator, we have something called as normal, like the normal rings. Okay, they are called slip rings because the brush is slipping on the on those rings. And in this case, we have split rings because there are holes in these rings, right? It is split. There is no, it is not a continuous ring. So this is how a DC generator. This is how an AC generator works. Okay. Just to recap, this is how an AC generator works. And since why is it AC? Because the direction of the current keeps changing. So alternating current, AC generator. Okay. And similarly, this is how a DC generator works, wherein the current direction does not change and the bulb is always glowing yellow. Over here, the current direction is changing, so the bulb is glowing blue and yellow. Okay, so what have we learned in this chapter? We learned how the magnetic field lines for various conductors look. Remember, like this loop conductor and the solenoid and all of that. We learned the right hand thumb rule. Okay, then we learned the which will give us the direction of the magnetic field. Then we learned about the force on a current carrying conductor, which gave us the Fleming's left hand rule. Okay, which will tell us how the direction of the force when there is a magnetic field and when there is current. Okay, we learned how an electric motor works. We looked at domestic electric circuits, how in India the potential difference is 220 volt between the red and the black wire. The red wire is neutral or negative. The black wire is neutral or negative. The red wire is live or positive, and the green wire is earth. We also learned electromagnetic induction, which gave us the Fleming's right hand rule. Okay, and we also learned how the electric generator works.